Welcome to ATMOS 5000, day number 31. We're focusing in on Stull, Chapter 8, Section 8.2. Specifically, we're going to be investigating the different types of satellite orbits that are used for weather satellites, and we'll talk about the instrumentation that's on the satellites, including the imagers and the sounders. So we have a satellite that's in orbit around the Earth. The satellite is experiencing microgravity. It's not that the gravity of Earth is any weaker. It's slightly weaker, but not substantially weaker at the altitude of the satellite. It's that the satellite is moving so fast that it has a centrifugal force which is equal and opposite to the gravitational force, resulting in a net force of essentially zero in the vertical. And in order to achieve this, it has to have a very high tangential velocity, orbital speeds, and we're going to calculate what those orbital speeds are here in class. So the centrifugal force is mass times the tangential velocity squared divided by the radius of curvature. And if we look at that in terms of the period of the orbit, t, then it's going to be 2 pi over the period of the orbit squared times mass times the radius. And the force of gravity, if we go back to Newton's formulation of gravity, it's the gravitational constant capital G times the mass of the Earth, in this case capital M, times the mass of the object divided by r squared. In easier parlance for us is to incorporate all of those Newtonian gravitational constants into a gravitational constant, lowercase g, gravity, and the force of gravity on the satellite is mass times that force of gravity, which is also a function of height. And gravity as a function of height is equal to the gravity at the surface of the Earth times a correction factor, which is r over r plus your altitude above the surface squared. And so we can use this equation, with g naught being 9.81 meters per second squared to determine the force of gravity at any altitude above the surface. And lastly, we can rearrange when we basically set these two forces equal to each other, the centrifugal force and the gravitational force, then you can actually solve for the period of the orbit, which is using the Newtonian gravitational constants. It's 2 pi r to the 3/2 divided by gm to the 1/2. Or if we use our vertically varying gravitational constant g of z, then it's simply 2 pi times the square root of the radius over the gravity at the altitude of the satellite. And most of the orbital for low Earth orbits range between about 70 minutes and 100 minutes for a full orbit, depending upon the altitude. So we have several different types of orbits that we can use for weather satellites. One of the more common ones is a polar orbiting satellite. These polar orbiting satellites are going to be in low Earth orbit, generally between about 700 kilometers and 1,600 kilometers, but low Earth orbit is kind of defined as less than 2,000 kilometers. And these polar orbiting satellites typically have a very significant orbital inclination, typically between about 98.5 and 99 degrees. So let's take a look at what inclination means. So if you were to launch a satellite from the equator and launch it due east, as in figure A down below, that would be an inclination of 0. If instead you launch it at an angle from the equator, then you can, a 45-degree angle will get you a 45 inclination, and a 99-degree inclination actually puts it past vertical, and so it's been inclined beyond the vertical, and it's moving primarily almost exactly over the North Pole, South Pole, off by a few degrees on each orbit. So why would we want to do a polar orbiting satellite? Well, basically, you can set it up so that it's in a sun-synchronous orbit, which is crossing the equator at the same time each orbit. So if you wanted to set your satellite to basically cross the equator at 10:30 in the morning, then you could set it up that way. If you wanted to be at 2:30 in the afternoon, you could set it up that way. If you wanted to be at 6 o'clock in the morning, you could do that. And we name the satellite orbits by the time at which they cross the equator. And so what's happening is that the satellite is orbiting in a plane, but the Earth is rotating underneath that plane. And so if you look in the first figure down below A, the satellite is crossing over position A, but on the second orbit, essentially kind of 100 minutes later, the Earth has rotated a certain amount, and we're now over position B. And on the third orbit, we'll be over position C. And all of these will essentially be still the same local time. On the descending orbit, we would be crossing, in this case, at looks like about 10:30 in the morning. And on the ascending orbit on the backside of the planet, it would be 10:30 at night. And this satellite would always pass over at those times because it's at a sun-synchronous orbit. And you can achieve that with an inclination between about 98.5 and 99 degrees. Polar orbiting satellites have some advantages, but they also have some disadvantages. One of the disadvantages is that they can't provide time-lapse images of storms due to the rotation of the Earth and their limited field of view. So you can see that from this figure, this satellite is actually basically tracing out swaths of areas on the Earth's surface that it can actually see. And although the satellite passes over the pole on each orbit, it only passes over a point on the equator a maximum of 2 times per day, once in the morning and once in the evening, or depending on how it's set up. And because these satellites are in low Earth orbit, they can't see the entire Earth. They can only see a fraction of the Earth from their altitude. And one of the consequences of this is that there are gaps in coverage of the satellite as it is moving along, and these gaps get bigger as you move from higher latitudes towards the equator, and the gaps can be quite large at the equator, which means that the satellite will not see each spot on the planet for 2 times a day at the equator, because there'll be certain spots that it misses. The other type of orbit that we use is a geostationary orbit, and these geostationary orbits put the satellite in orbit around the equatorial plane, so it has an inclination of 0, and it's in the direction of the Earth's rotation, and it rotates once every 24 hours. And as a result, the GOES satellite remains in orbit over a specific geographic location. And the way that we use these GOES satellites is we can continuously monitor for visible light, infrared, and we can monitor for water vapor in the Earth's atmosphere using a combination of imagers and sounders that we'll go into in more detail here. So here we have an animation. We're looking down at the Earth, which is the blue dot. We're looking down at the North Pole, and the brown dot on the Earth, it represents a geographic location, and the Earth is rotating once every 24 hours. And the green dot, tracing out the red orbit, is the geostationary satellite. It's orbiting once every 24 hours, so it remains fixed in space relative to that geographic location on the Earth. And this can only happen when the satellite is orbiting in the equatorial plane. The distance at which this orbital period is matched is a little over 22,000 miles. And at that distance, the satellite can see a full disk of the planet, so it can see half of the Earth from that altitude. So how do we use these GOES satellites? Well, we use them to identify our cloud coverage, and by combining the visible and the infrared images, we can also determine the types of clouds and the height of the clouds. One of the more useful things from the GOES satellites is that they can provide us with a time-lapse image of cloud motion and development in the atmosphere. They are our primary eyes over the oceans, and they help us identify the location of tropical storms and hurricanes, where they can identify moist and dry regions of the atmosphere, and they really provide some of the only data that we have over the oceans, which is kind of nice. So here's an example of a GOES visible image from 22,000 miles. And you can notice that the satellite perspective is from above the equator, and although the satellite can see half of the planet, it's very difficult to discern what's going on around the edges because of the angle at which the Earth is curving away from the satellite. So this satellite does a good job of seeing what is in the latitudes and longitudes, the longitudes over which it is directly sitting. But as you move further away from that, the view gets more and more distorted. And on this one, you can't quite see the full half disk because the sun is only illuminating portion of this. And that's one of the problems with the visible imager in that it only provides useful data during the sunlight hours, during the daylight hours. So here we have the same image that is looking at the infrared heat energy coming from the Earth. And this one, you can see that space is white because it's very cold. On this images, white is denoted as cold temperatures and dark is warm temperatures. So we can see that Argentina down in South America is very warm without much cloud cover, and so it's showing up as dark. The ocean just north of South America doesn't have many clouds over it, and it's darker, so it's a warmer ocean. The really white things that you see are high-level clouds that are very cold, that are not emitting a lot of radiation because of their cold temperature. So here we're looking at a infrared image from the continental United States, and looking at this, we're able to diagnose areas that are cloud-free, like Mexico and western Texas. The Gulf of Mexico doesn't appear to have many clouds in it, although if the clouds are really low, the clouds are going to be about the same temperature as the sea surface, and in that case, the clouds would be invisible on the infrared image, and the only way we could see those would be to look at the visible image to see if there were bright white reflecting clouds over the ocean in that region. Up near New England, near just southeast of New York City and New Jersey, we have a mid-layer cloud deck, which is kind of a light gray. And then we can also see the comma cloud associated with the low pressure zone on the eastern coast of the United States that has high cloud coverage, which is the bright white that is looking like an arc. And then there's high clouds over much of the Midwest as well. If we look at the water vapor, the way that the water vapor image is described is that the things that are dark are very dry, and things that are white have a lot of water. Now that water can be in the form of liquid water, ice, or water vapor. This particular channel doesn't distinguish between those, so it just kind of looks at the column integrated amount of water and doesn't tell you anything about whether it's low elevation water vapor or high elevation water vapor. We need to have a sounder for that, but this is strictly an imager, which is looking at the radiation that comes up to the satellite from a single channel. And we have that low pressure zone on the east coast of the United States, and you can see that it's pulling up a lot of tropical moisture from the Gulf of Mexico and wrapping around the storm, but it's also pulling dry air from Mexico into the storm as well. And so you have this very distinct boundary that you can see that's happening over Florida. The southern part of Florida has a lot of water vapor in the atmosphere, and the northern part of Florida doesn't. And then you can see that dry air being pulled into the storm off the coast of the United States. So the question that I have is, how many GOES satellites do we really need to get global coverage? So we're looking at the Earth again from a perspective in space over the North Pole. And so let's start off with 2 satellites. So we have 2 polar orbiting satellites, Satellite 1 and Satellite 2. What can they see? Well, Satellite 1 can see that side of the planet. Satellite 2 can see that side of the planet. They're essentially seeing half of the planet, but they're not seeing the areas on the wings very effectively. So we have to add more satellites in order to get the coverage on all quadrants of the Earth. And if we add 2 more global GOES satellites, then we can have really strong coverage on each quadrant. Now, technically, you can probably get away with 3 geostationary satellites, but to have really good coverage, and we really want to have at least 4 GOES satellites in order to get nice coverage without limb effects, limiting our ability to understand what's going on. So what geostationary satellites do we have? Well, as of March 2017, the United States has 4 GOES satellites in orbit. We have 2 that are operational, GOES East and GOES West. One is looking at the Pacific Ocean, one is looking at the Atlantic Ocean. And then we have essentially 2 that are spares in orbit, ready to go should GOES 13 or GOES 15 die. The European Union has 3 plus a spare. They have 1 that's over the Indian Ocean and 1 that is over essentially the 0-degree Greenwich line that passes straight over the UK. And they have 2 there. They have a regular one and then have a rapid scan one as well. Japan has 2 in orbit. They have 1 and a spare. It's located over the Western Pacific. China has 3 that are covering most of Asia. Russia has 1 and India has 1 as well. But some of those are in very similar orbits, so they provide very similar information. So let's take a look at the different imager channels. Imager basically means that we have a sensor that is looking at different wavelengths of radiation. So the GOES 16 satellite happens to have 16 channels. That's not how they're named, but this happens to be the 16th GOES satellite, and it happens to have 16 channels. Coincidence? It starts off with channels 1 and 2, which are looking at visible wavelengths, the red and the blue wavelengths, and then moves on into infrared. All of the other channels, channels 3 through 16, are all in the infrared, ranging from the near infrared to the atmospheric window, up around 10 micrometers. And the nickname or the spectral band kind of tells what some of these wavelengths are used for, and primarily the ones that we use, that we see for the visible, the infrared, and the water vapor are basically channels 2, channels 8, and channels 13. So 2 is our visible band, 8 is our water vapor band, and 13 is our infrared band that we were basically describing in the previous images. So here we have a portion of the disk associated with the GOES satellite, and this happens to be a visible image. So the bright images are clouds, obviously. The dark images are places where you can see through the clouds to either the ocean surface or the ground cover. And it is possible that you can see white on the Earth's surface, which would be either snow or ice as well. The visible image provides a very good synopsis of where the clouds are, but it doesn't tell you anything necessarily about the altitude of the clouds. So for example, if you look at the spot labeled A just off the coast of Baja California, we have a broad region of white clouds. but we don't know if those are low clouds or high clouds. As opposed to out in the central Pacific, the place labeled U, we have a very bright cloud band, but it's hard to tell from this particular image on whether or not those happen to be high clouds or low clouds. To differentiate that, we would have to look at the infrared image, and low clouds will be emitting more radiation because they're warmer, and high clouds will be emitting less radiation because they are at an altitude where it's colder. So by combining the visible and the infrared, you can actually get information about cloud height. So let's take a look at the next image, which is, it should be an infrared image. Aha! So that area A off the coast of Baja California is a very light gray, which means that it is a warmer cloud deck. It's not nearly as warm as the ground of North America, and so what we're looking at there is essentially a low to medium cloud deck. And then U, out in the Central Pacific, is bright white, which means in this infrared image, that's not much energy is making it to the satellite, which means that those are very high clouds out over the Central Pacific at position U. And by toggling back and forth between the visible and the infrared image, you can identify where the clouds are at and what altitudes they are most likely at as well. And then you have the water vapor, and the water vapor can tell you where the atmosphere is particularly dry or particularly wet. And you can see the advection of moisture on the time-lapse image of the water vapor loop. So let's look at the imager channels. So channels 1 and 2, which are visible light, they're really good at identifying clouds and cloud-free areas during the day. Unfortunately, they are useless at night because there's no reflected visible light to look at. However, they can produce time-lapse sequences during the day, which are very helpful in understanding the evolution and formation of thunderstorms, but also in the progression of fronts. And they also can provide us with wonderful information out over the oceans where we don't have direct observations. If we look at channel 13, which is our far infrared, which occurs in that atmospheric window, so it's using the infrared in that transmittance window so we can see through the atmosphere, and it can see all the way down to the surface if there are no clouds, and if there are clouds, it can see down to the top of those clouds. And we use this channel to determine the temperatures of the cloud top, the sea surface, or the ground. The advantage of the infrared is that the Earth is constantly giving off heat energy, so it doesn't matter what time of day. The infrared imager can basically see the Earth in the infrared 24 hours a day, and because it can do that, it can provide uninterrupted time-lapse sequences that are not limited by sunlight or time of day. The water vapor can basically be taken from channels 8, 9, or 10, but it's typically taken from channel 8 for the images that we've been looking at. And in this part of the spectrum, water is a good absorber. It's essentially a shoulder region of the absorption spectrum. So the more water vapor there is, the more absorption that there is, the less transmission. And we can use the amount of infrared heat energy that is received by the satellite to determine the column abundance, which is basically the total amount of water vapor in the atmosphere. It's not just water vapor, it could be liquid or ice as well. And similar to the infrared channel, channel 13, this one provides a signal 24 hours a day because the Earth is always emitting this infrared radiation, and it can also be used for time-lapse sequences looking at the advection of water vapor as well. So what is the difference between an imager and a sounder? Well, an imager is basically a detector that is looking at a single wavelength only. If you are instead have multiple wavelengths. You essentially have multiple measurements. And as we saw before when we were looking at the weights of the atmospheric atmosphere at different wavelengths, then, for example, here we have water vapor loops, water vapor imagers for channel 8, 9, and 10, and they are sensitive to different altitudes in the Earth's atmosphere. And if you combine the information from these three different altitude weightings, we can do what's called a retrieval, and that retrieval algorithm will allow us to get some information about the vertical variation of the quantity that's being measured. So in this case, channels 8, 9, and 10 are looking at water vapor water absorption in the Earth's atmosphere. So rather than look at a total column abundance, it can give us information about the amount of water vapor that's at high, medium, and lower altitudes, which gives us vertical sounding information from a satellite. It's very coarse. It does not provide the level of detail that a Ray-Winson balloon would, but it can provide information over the oceans in areas where you don't have Ray-Winson launches. So there are two corollaries that we have to understand. So here is corollary number 1, and it basically responds to the situation, idealized situation that we have down below, where we have 4 different wavelength ranges that have non-overlapping weighting functions. Channel 1 is sensitive to the area of the atmosphere between 15 and 20 kilometers. Channel 2 is sensitive between 10 and 15, channel 3 between 5 and 10, and channel 4 between 0 and 5. So this is a very idealized situation. And if you have these 4 channels that don't overlap, the retrieval corollary basically says that at most, the sounder can retrieve 1 piece of temperature data, or basically 1 measurement per data channel. And if we're looking at temperature, so the temperature that it gives for that channel is the average brightness temperature weighted over the depth of the weighting function. So on the right, we have the circles with the lines, which would be like your Ray-Winson data, which is very high resolution temperature as a function of height. But the satellite can give you 1 piece of information for each window. So instead of getting the detail that you get from the balloon launch, you get a general idea of how the temperature, the average temperature is in each of those 4 layers. So you essentially have 4 data points in the sounder, whereas in the balloon launch, you'll have tens, if not 100 different layers on the way up. The problem is that most of our weighting functions are overlapping, and corollary number 2 for the retrieval basically is that if your weighting functions from different channels overlap in different altitudes, then they don't provide truly independent observations, and as a result, the sounding can retrieve fewer than 1 piece of temperature or measurement data per channel. So it's really difficult to get accurate and detailed vertical sounding information from satellites because of the retrieval corollaries number 1 and number 2. But they do provide useful information nonetheless. It's just much more coarse than we get from our balloon launches.